Good morning, afternoon, evening, or night, people. Welcome to Indirect Measurement, when you can't measure something directly because a tape measure just won't stretch to there, okay? Here's a diagram of a tree. If we want to find the height of it and we have some information, we can use maths, okay? So there are three common methods. The first one is similar triangle ratios. Shadows and mirrors, that sounds magical, but it's really just mathemagic maybe. Similar triangles could also be used to find things like the distance across a lake or the distance that a tunnel needs to be dug through a mountain. But today's examples are all having to do with things that are tall, okay? So another method is right angles and geometric mean. And then another method is clinometers and trigonometry. A lot of people argue that this one is the most accurate, but that's okay. Let's see what we have here. This first example is from similar triangle ratio shadows. When we're talking about shadows, it is important to recognize that if the sun is shining, okay, for objects that are near each other, relatively near each other on Earth, the angle that is made with the tip of the shadow towards the sun is the same for all objects that are near each other at the same time of day, right? Okay. So the other thing that we can capitalize on for this is that things that go up and down are usually perpendicular to the Earth. So we have right angles over here. If we have right angles, it's clear we're looking at triangles, and these triangles have angle-angle similarity, okay? And that is because when I subtract from 180 the two angles that I have, these last angles have to be the same. Formally stated, if two angles of one triangle are the same as two angles of another triangle, then the third angles must be the same, and the triangles have the exact same shape. They might be different sizes, as you can see here. These are different sizes. But because they're the exact same shape, that means that their sides are proportional. Proportions like kittens are to cats as puppies are to dogs. Okay, in this case, we're going to have the man is to the lamp as the man's shadow is to the lamp's shadow, or the small shadow to the large shadow. Okay, and so we have numbers for these. Let's go ahead and plug them in and substitute. I'm going to say first take out the shadows, and we have the man shadow 6 feet. The lamp shadow is 18 feet. And now let's replace the man and the lamp. The man is 5 1/4 feet, and the lamp is X feet. Okay, to solve this, let's first get rid of units. And whenever I'm solving a proportion, normally I just cross multiply, but it might be advantageous to reduce. 6/18, divide both of them by 6, and we get 1/3, which is convenient. We got to get X by itself, but I'm going to get this 3 off the bottom first by multiplying both sides by 3 and seeing those go away. And now I have just 1 equals 3 5.25s over x. So I'm going to multiply both sides by x, and now x is by itself, or at least it has a 1 next to it, which means it's 1x or a x equals 3 5 1/4 is 15.75 feet. That's how tall that lamppost was. You probably could have measured that with a tape measure, maybe. I don't know if you could get it to stay rigid and go that high up. I don't know. It might be impossible. But remember to box your answer, okay? All right. Another one with similar triangle ratios. This time it's a mirror. So here we have a mirror. The guy is looking down the line of the mirror, and he is seeing in the mirror the reflection of the top of some random tower that no one could ever know what it was. Just kidding, that's the Eiffel Tower in Paris. So anyway, something about mirrors, people. If you draw this line perpendicular to the mirror, you create two angles. On this side, it's called the angle of incidence. On this side, it's the angle of reflection. And those are always equal to each other. Because those are equal, their complements down here are also going to be equal. Okay, so that's that therefore. The other part we need to remember is that things that go up and down are perpendicular. So both of these have their own right angles. And once again, we have angle-angle similarity because we have two triangles with two angles that are the same in both. Okay, so if I knew something about the ground lengths, for instance, and this is something I could measure with a tape measure or some other device, but that might be easier than trying to put a tape measure up the Eiffel Tower. I could say that I have the ground parts. And if I have the ground parts, this is the beginning of a proportion. So I'm going to put the ground parts in there as 14 1/4 feet is to 2,524.625 feet. Okay. And then I have the up and down bits. I'm calling those the tall parts. Okay. The tall parts, let's say this man is 6 feet and the Eiffel Tower is X feet. On this proportion, I'm going to solve it more traditionally. That is to say, I'm going to multiply both sides by the denominators, okay, canceling them out on the sides that they are. So that's going to bring the X up here and put it next to the 14.25. That's going to take the 2,524.625 and put it next to the 6, okay? And I'm not even going to look at what this product right here is. I don't need to, because really I just need to undo multiplication over here to get X by itself. So I'm going to divide both sides by 14.25, and this is what I'm throwing into my calculator on Desmos. So heading over to Desmos, 6 times 2,524.625, click the divide button, 14.25. I get 1063, or 1,063 feet is how tall the Eiffel Tower is. Box that. And you know what? Pause. Go look it up. See if that's true. Okay. So if you Google how tall is my tree, or how do I find out how tall my tree is, you get so many diagrams of similar triangles having to do with shadows that I just had to show some of these to you guys. This is apparently a very common issue that people have. And why would they? If you want to fell a tree and chop it down, you need to worry about its damage radius. You need to worry about how tall it is so that you know where it could potentially fall, because you do not want to crush your neighbor's car or your neighbor's garage because you didn't know your tree was so tall, right? So this is very important. All right, so this is method 2, right angles and geometric mean. So down here we have a right angle and a figurative triangle. You will not need a triangle that is as big as this flagpole, okay? Instead, and then we have this thing right here. This is like an altitude of this triangle drawn to the hypotenuse from the right angle. It is called the geometric mean, okay? So we'll see what that means. What we need is a right angle, and you guys all know what this is. This is one of your speed squares or Carpenter squares, and you're going to take this right angle and you're going to use it. Ooh, look at that animation. We are living in the future, people. I am fancy. You're going to put that thing up to your eye such that looking down one direction, you see the bottom of the thing you're measuring, and looking along the other direction, you see the top of the thing that you're measuring, okay? And that's really going to be how easy it is. But this point right here is what we need to find out two distances on. We need to know how high up your eyeball is, which you can just use a measuring tape for. And we need to figure out how far away your eyeball is from the thing that you're measuring. You might need a friend for this so that you can stand super still while you're holding your right angle. This right angle could be a piece of paper, people. Because these are the two measurements that you need to do this technique, okay? Let's see why this works. I've drawn two triangles, and I'm going to put an acute angle down in one of them. This is a green acute angle. What I want you to consider is that for the original big one, it had this green acute angle. The other acute angle was its complement when I subtract from 90 degrees. Well, if I subtract from 90 degrees and I get this light green complement, and then from there I subtract from 90 degrees, I get the dark green complement over here, okay? So these triangles have all the same angles in them, and we're going to capitalize on that. So look at this fancy animation, people. I'm taking those triangles and I'm floating them over here, right? So We have angle-angle similarity again, yay. And let's identify what we've already measured. We have the geometric mean, that is the distance from your eyeball to the thing. It's going to be these two lengths. We have the how high up your eyeball is. And the only thing that we don't have here corresponds to the remaining length of our flagpole, okay? And so, it looks like we're ready to do a proportion, okay? And so kittens are to cats as puppies are to dogs situation. In this case, it's going to be the top part of the flagpole is to the geometric mean, as the geometric mean is to the eyeball height. If we had numbers for this, like let's say that your eyeball is 5.5 feet off the ground and you're 12 feet away from your object, we can just throw those information in, and notice we have one thing to solve for, just the remaining top half. It is being divided, and so we're going to draw our line, and we're going to multiply both sides by 12. I did not draw my line. 12 12s is 144, divided by 5.5 gives us 26.18. But we have to be careful. That's only the top part of the flagpole. We need to add in the 5.5 more feet, taking us up to 31.68 feet total for the flagpole. Yay! Cool. All right, this clinometers and trigonometry. This is our third technique, okay? So we have a couple of things. We have a line of sight to the top of the tree. We have an angle of elevation, and we have the horizontal. Horizontal, think horizon, where the sun rises, okay? We can calculate the eyeball height very easily, which is going to be a portion of our tree, okay? We can also calculate this ground distance from your eyeball to the object. It's like an adjacent in this triangle, okay? So when I say adjacent, here's our angle right here. This side is next to it. The thing we don't have is this unknown opposite side up here. We'll call that x later, okay? And we have this angle, okay? So let's see here, guys. What trig function am I going to apply? We have so, ka, toa. Some old horse caught another horse, taking oats away. And it looks like the line of sight is not going to be measurable, so we have no hypotenuse. Cancel out the hypotenuses, and that means no so, no ka. This is a toa problem, okay? The tangent of this angle is going to be equal to the opposite that we do not know, that's x, okay, divided by the adjacent that we measured, this distance right here, okay? The problem is once I solve for x, it's being divided by some number, the adjacent. If I multiply both sides, I get x by itself. In other words, x is equal to the adjacent times the tangent of the angle. But where I might have the adjacent because I measured, how do I get that angle? Well, this is what we have. We have a device called a clinometer, okay? And so if it were horizontal, like flat, okay, this is a string, and it would be hanging down this direction right here. When you bring it to an angle of elevation, okay, when you turn this thing, the weight moves, and the weight moves from here over to here. And then you can get a reading on this angle, okay? What you need to recognize is that this angle is the same as this angle here. So it ends up being our angle of elevation. And by the way, on a lot of protractors, this is 90 degrees. So to figure out this angle, you might have to do a little addition or subtraction, okay? And this looks very much like a high school clinometer. It's got your protractor and scotch tape and a straw to look through. It's real cute. Anyway, so go out, find your angle that way. Once you know your angle, we just have to plug stuff in. So let's say that the eyeball height was 5.5 feet. Let's say that the adjacent part was 20 feet. Sorry, I forgot to write feet. And let's say that the angle of elevation was 30, okay? So dropping that information that we have in, we get that x, this unknown opposite part up here, is 20 tangent 30. Plug that into a calculator and you get some number. I'm not going to worry about that because then I'd have to add in the eyeball height, and I'm all about doing that ahead of time. So really it's going to be the tree, sorry, this is a tree. is equal to the eyeball height plus that x part. Heading over to Desmos, we see that that is 17.04700538. I'm just kidding. It's 17 feet, people. 17 feet. Cool. This looks like 3 petals traveling around a circle. But if you look closely, guys, this is just individual dots moving in and out and in and out. So this is an illusion of movement created by other things moving. Each of these dots is moving in a harmonic pattern defined by a trigonometric sinusoidal wave. Trigonometry is some exciting math we're getting into. Yay,